Okay, let's go over practice exam 2, number 8. Right. So first, part A, we want to find the x-intercept and y-intercept. Right. To find the x-intercept, we set the y equal to 0, which means that to basically set the whole function equal to 0. Then, in order to make the fraction equal to 0, we just have to make sure that the numerator equal to 0. And solve that, then you get the, add 3 to both sides and divide through by 2. You get the 3 halves as the x-intercept, right? And the y-intercept, in order to find the y-intercept, we set x equal to 0. So we plug in x equals 0 into the function. So you can see that I put 0 here, and you have a negative 3. So you have a negative 3 here, over, put 0 here, so that's going to be 0, so you have a negative 3. So negative 3 over 3 is 1, so that's why y-intercept is 1. Alright, so we can actually mark those points. So 2/3 is the x-intercept, so you can see that here, maybe I'll use a different color here. So you can see that we can put a dot right there, right? And y-intercept is 1, so we can put a dot right there. Right? Then we'll see that for part B, we want to find a horizontal asymptote and a vertical asymptote. So in order to find a horizontal asymptote, we take the limit as x approaches either positive infinity or negative infinity. Right? So since we have, let's say on top, 2x is the leading term, and x is a leading term, so at 2x over x, then take the limit, but x is cancelled out, so it gives you 2. So horizontal asymptote is y equals 2. Right, so we have that. Right, vertical asymptote. So vertical asymptote is where the function either blows up to positive infinity or blows down to negative infinity. So easiest way to have that is having a 0 on the denominator. So we set the denominator equal to 0, so we can easily find x equals 3. Right, so those are the vertical asymptotes and the horizontal asymptotes. So we mark those by putting a horizontal asymptote here. You can see that the horizontal asymptote x equals 2. So here, this is 2 right there. So you have a horizontal asymptote there, right? And x equals 3. So you can see that this is 3 right here. So this is a vertical asymptote. All right. So we have a horizontal asymptote and a vertical asymptote. All right, then we're going to have to look at the first derivative and the second derivative to determine the sign of the derivative and the second derivative. All right, so first derivative is actually given right here, so we don't have to compute. And the same way, second derivative is given right here. All right, so we can just look at the sign. So we're going to divide the whole interval at 3, because the 3, the domain of the original function is all real numbers except for 3. So x cannot be equal to 3. All right, so divide into 2 intervals, which is negative infinity 3 and the 3 to positive infinity. Right, so we can try any number less than 3. So I'll probably try 0. So we look at f prime of 0, right? So if you plug in 0 here, you see that the negative 3 squared, so bottom is positive. Right, top is negative 3, it's negative. So if you plug in x equals 0 into the first derivative, it's actually negative. So that's why we have a negative sign there, right? And if you look at the second derivative, say at 0, right? So you have the 6 on top is definitely positive. On the bottom is negative 3 cubed, so that's negative. So you see that this is going to be negative, right? So that's why you have a negative sign there, right? if you try something bigger than 3, so let's try f prime of 4, for example, and the top is still negative, and a 4 minus 3 is still positive, so it's going to be negative, right? So it's still negative here, right? And f double prime of 4, right, will give you 6 on top is positive, 4 minus 3 is cubed is positive, so positive over positive is actually positive, so you have a positive sign there. All right, so which means that you will have, so on this interval, negative infinity to 3, you have, so f, original function, will have this shape. So this indicates that it's decreasing and a concave down. So you have a shape like that, right? On interval 3 to infinity, it's decreasing and concave up. So you see that the shape is like that. All right, so we just have to kind of draw those, draw the graph of this original function following the shape indicated by the first derivative and the second derivative. So let's do that. All right, I'll probably use a red so that we can see it. All right, so we know that we have to go through these 2 points, and we have to have a horizontal asymptote there and a vertical asymptote there. So we can see that the graph is going to go like this, as we did. All right, so that. All right, since it's nice to have some reference points, so maybe I'll try some values. So we can try. So what I did was I basically pick, let's say, a random number. So I picked, let's see, this is 3, 4, 5, 6. Right, so I picked 6. Right, so plug it in and plug it into the original function. So f of 6 is equal to, right, so plug in 6, 2 times 6, 12, minus 3 is 9, divided by 6 minus 3 is 3, right? So that will give you 3. So I go 6, 1, 2, 3, so I put a dot there, right? Then maybe I wanted another point, and I actually picked, let's see, seems like I picked 4.5, so f of 4.5, so 4.5, which came out to be a fairly nice number. So 4.5 times 2 is 9, minus 3 is 6, right, divided by, and 4.5 minus 3 is 1.5, which gives you 4. So that's probably why I chose that. So 4.5 is right here, and go up, and the y value is 4. So it's, let's see, this is 2, 3, 4. 4 is right here. Right, so that's why I put a dot there. And you don't have to choose these 2 points. I thought that those are nice points, so I chose them. Right, and after that, we just have to make sure to go through those 2 points and follow the shape. So on that interval, it has to be decreasing and a concave up. So that's why we have a graph which looks kind of like this. All right, so that's how we got the graph of the original function, which is a rational function. All right, that's it. I hope that this was clear.